These are examples from Lesson 3.3, Triangles, Parallel Lines, and Constructions. In this video, you will learn how parallel and perpendicular lines relate to each other, how to prove parallel and perpendicular lines, and how to use various properties of parallel and perpendicular lines to solve real-world problems. Example 1. In this example, you will prove the converse of a theorem. Now, we've proved theorems, but we haven't proved the converse of parallel lines or lines cut by transversal type theorems. Now, recall, when using converses of parallel line theorems, your conclusion is always that the lines have to be parallel. And this is why the prove statement here is that two lines are parallel. So what we're doing here is we're saying, okay, we've got two lines cut by transversal, and they're telling us that angle 1 and 7 are congruent. Well, angles 1 and 7 are alternate exterior angles, because that's what we're trying to prove, the alternate exterior angles converse. So we need to show that two of those are congruent, which we've done here. And then in the conclusion is this line here, L and M are parallel. So we're going in reverse as indicated by the lesson we had on this particular thing. And so here we begin. We've got given angle 1 is congruent to angle 7 given to us. And from this point we notice that angles 1 and 3 are vertical angles, and vertical angles are congruent with the vertical angles congruence theorem. So angle 1 is congruent to angle 3 by the vertical angles congruence theorem. And from that point we have the statement angle 3 is congruent to angle 7. Notice how they took statements 2 and 1. If angle 3 is congruent to angle 1 and angle 1 is congruent to angle 7, then angle 3 must be congruent to angle 7. So we took these two and produced this one. Which property is that? The transitive property of congruence. And we use statements 2 and 1. Now that we've done that, we're showing that angle 3 is congruent to angle 7. What kind of angles are these? They're corresponding angles. Lower right, lower right. They're matching positions. So, by the postulate that says that if you have corresponding angles that are congruent, then the two lines cut by the transversal are parallel, we can go straight to this statement now. Line L is parallel to line M by the corresponding angles converse. Once again, if angles 3 and 7 are congruent, then it forces these two lines, L and M, to be parallel by the converse of the corresponding angles postulate. Example 2. In this example, you will apply the parallel lines converses. Which lines are parallel in the diagram if angle 1 is congruent to angle 2? Justify your answer. And which lines are parallel in the diagram if the measure of angle 1 plus the measure of angle 5 equals 180 degrees? Justify your answer. So starting with the first part. Notice we've got two sets of lines that are being intersected. So this may be one of those problems where we have to determine which three of the four lines we're going to be using in each case. So here we go with the first part. Which lines are parallel, L and M or A and B, if angles 1 and 2 are congruent? So let's come over here. Angle 1 is congruent to angle 2. Now we're using these two angles, so we take the lines that are a part of those angles. Line M is definitely part of both of them, so we're using that line. We're using line A because it makes up this angle 1, and we're using line B because it's making up line 2, so we can cover up line L, at least mentally. Notice the two lines cut by the transversal. These are corresponding angles because they're in the same matching position, upper right, upper right. So we can say that A is parallel to B. Line A is parallel to B by, justify our answer, by the corresponding angles converse. Now they didn't ask for this, but the transversal that was being used here was line M. Okay, the second part. Starting all over, which lines are parallel in the diagram if the measure of angle 1 plus the measure of angle 5 is 180 degrees? Well, that's the definition of supplementary angles. So if these two angles are supplementary, they should be inside two lines. That would make them same side interior angles. So let's figure out which lines we're going to use. Obviously, we're going to use line A because line A creates both these angles in part. And then, of course, line L and M are creating these two angles. So line B is the line that we're not using. So here we've got these two lines cut by this transversal. These angles, which are on the same side of the transversal, they add to 180, so they're supplementary. So by the same side angles converse, we know that line L is parallel to line M. By the same side interior angles converse. And the transversal happens to be line A here. It's cutting the two lines. Example 3. In this example, you will apply a parallel line's converse. The fence gate at the right is made up of pieces of wood arranged in various directions. Suppose angle 1 and angle 2 are congruent. Our lines R and S parallel. Why? So taking a look at our gate here, our diagram, our photograph, we've got line R and line S are a couple of the pickets, and then line T, the transversal, is this cross piece of wood that holds it together through the middle. So let's go ahead and mark our drawing. Angles 1 and 2 are congruent. That's angle 1 here and angle 2 here. Notice these two lines cut by the transversal. These must be alternate exterior angles. If alternate exterior angles are congruent, the two lines must be parallel. So our lines R and S parallel? Yes. S is parallel to R. Why? By the alternate exterior angles converse. Example 4. In example 4, you'll use parallel lines converse, or parallel lines converse that contains an algebraic expression. Find the missing value x for which line A is parallel to line B. Also, find the measure of the missing angle. Let's take this first sentence. It says, find the value of x for which A is parallel to B. The language is a little different than what we're used to. That's because what they're asking for is what is the value for this variable that causes this angle here and this angle here to be supplementary because they're on one side of the transversal inside the two lines. So we want to figure out what value for x that must be so that these are supplementary. That will cause these two lines to be parallel. So it's just the reverse of what we did in the previous lesson. So that's why the language is a little bit different. So what I'm going to write here to make that very clear is that I'm going to write for A, line A to be parallel to line B, same side, interior angles must be what? supplementary. So we take the measure for this angle here and force it to be equal to, or excuse me, force it to be supplementary with this angle here. So that would mean we'd have 2x plus 9 degrees. We would add the measure of this angle, 111 degrees, and cause it to both, the sum of it both equal 180 degrees. And then whatever we get for x is the value that causes this to be supplementary with that, thereby making these two lines parallel. So solving this equation, we drop the parentheses and combine like terms. So we have 2x plus 9 plus 111 is 120. Subtract 120 from both sides, and 2x equals 60. Divide both sides by 2, and x is 30. And so I'm going to write x must be 30 for A to be parallel to B. Okay, and then figuring out what this angle is, we can take 2x plus 9 degrees, whatever the measure of that is, and substitute in the value for x. We have 2 times 30 plus 9 degrees. 2 times 30 is 60 plus 9 degrees, which gives us 69 degrees. And to check it, you can add 111 to 69 and you should get 180. Example 5. In example 5, you'll prove a theorem involving a combination of parallel and perpendicular lines. So we're on to those particular set of theorems. All right. So here we have the perpendicular transversal theorem, which states in a plane, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other line. So let's see if our given information matches the hypothesis P. It says J is perpendicular to H and H is parallel to K. Let's check that out. Remember, the hypothesis again is in a plane. If a line is perpendicular to one of two lines, well, J is perpendicular to H. It's perpendicular to one of two other lines that are parallel. And it says H is parallel to K. These are parallel. So that's a perfect setup for the hypothesis here. And we want to prove, as the theorem states, that it is also perpendicular to the other. Well, what is it? The it is the transversal. J was perpendicular to H. We want to see if it, J, is also perpendicular to the other line, K. So this is what we're trying to prove. So starting off, we have our given information. Line J is perpendicular to line H, and line H is parallel to line K. It's all given to us. We've marked our drawing. Make sure you mark your diagram as you go. It can be extremely helpful in a proof if you'll do that as you go. Okay, then statement 2, we have the measure of angle 2 is 90 degrees. Where did they get that? So come over here to angle 2. We marked it with a right angle symbol because they told us up here that H was perpendicular to J, or J is perpendicular to H. So if two lines are perpendicular, then the angles are right. And if the angles are right, they measure 90 degrees. So this is the definition of perpendicular lines. Okay, if the measure of angle 2 is 90 degrees, then we move on to the next statement. Doesn't seem, it has a little bit to do with statement 2, but it suddenly switches over to angle 6. It says angle 2 is congruent to angle 6. Okay, now without even looking at the fact that angle 2 is a right angle, let's just look at where 2 and 6 are. Are these corresponding angles? These are two lines cut by a transversal, two parallel lines cut by a transversal. And these two angles must be congruent because they're upper right, corresponding angles. Well, the lines are already parallel. So if two parallel lines are cut by a transversal, then corresponding angles are congruent. That is the original corresponding angles postulate. It's not the converse. So that's the reason here. We can make this statement. Angle 2 is congruent to angle 6 by the corresponding angles postulate. The original postulate. So now, since we know this one's congruent to this one, let's go ahead and write that there. And 4, the reason for this next statement is the definition of congruent angles. Well, the previous statement we just had was angle 2 is congruent to angle 6, and this is already in terms of measurements and equality. So it looks like they're trying to get us to change this to this. If two angles are congruent, then their measures are equal. Definition of congruent angles. So from here to here, we got that. Okay, so again, we know these are congruent up here. And then the measure of angle 6 is 90 degrees. Well, we know that 2 and 6 were congruent, and since 2 is a right angle, doesn't 6 have to be a right angle? So what they're doing is they're using the transitive property here. They're taking this statement right here, feeds into that one, and they're taking this one right here, and they're saying if the measure of angle 6 is equal to the measure of angle 2, and the measure of angle 2 equals 90 degrees, then the measure of angle 6 is equal to 90 degrees. Transitive property of, and its equality. And we use statements 2 and 4. Now that we know this is a right angle, if this is a right angle, the two lines it involves are lines J and K. So if angle 6 is 90 degrees, therefore line J must be perpendicular to line K. And that again was the definition of perpendicular lines. And we have just proved the perpendicular transversal theorem. Example 6. In example 6, you'll prove a geometric statement that involves a combination of parallel and perpendicular lines. So this is kind of the same sort of proof that we just had in example 5, so that's a little bit different. Prove the relationship between the two indicated lines. Here we have our diagram with about 4 different lines in it. We're given quite a bit of information here. We want to prove that C is perpendicular to A. Looks like it doesn't reach A, but it really does because there's an arrow on it. Lines go on forever in both directions. So if we need to, we can extend this line. But that's what we want to prove. And we're given all this information to do it, and that kind of helps us out a little bit. So let's take it statement by statement, reason by reason, and use some logic here. Okay. Keep track as we go. It's like I'm going to show you, as with each statement or with each geometric statement, we mark our drawing. Alright, given C is perpendicular to B, locate C, locate B. They're perpendicular, so let's write a right angle symbol there. B and D are perpendicular, so B and D perpendicular, right angle symbol there. I'm going to stop right there before we get to the third one. They've just used these first two for their given. So we've just taken care of that. It was given to us in the proof. From these two, what can we conclude from this statement here with these two items in it? If C is perpendicular to B and D is perpendicular to B, what does it say about these two lines? Why, that they're parallel. You recognize that theorem? So we can say C and D are parallel. And then to figure out which theorem we use, if one line is perpendicular to a line and another line is perpendicular to that same line, then those two lines are parallel. You can either write that all out, or you can just use the title of it, which is the lines perpendicular to a transversal theorem. that enabled us to make this statement. Now we've already drawn it on our figure, just like I mentioned before. Now there's really not much we can do with what we just concluded. Let's go on to the rest of our given information. D is perpendicular to A. That's our next one. D is perpendicular to A. So let's mark it on our drawing. D and A are perpendicular. We write a right angle symbol right there, or on one of the angles there. And we want to conclude, it looks like we're supposed to be able to conclude C is perpendicular to A. Let's see if we can do that. If D is perpendicular to B, let's see, and we got C, let's go ahead and extend C. Since we're going to state somehow that C and A have something to do with each other, I use an auxiliary line here, dashed. Okay, so what we can say is, if you have D is perpendicular to A, and you already know that these are two parallel lines, we just showed it here, then what does that say about this line and the other line that's parallel to this one? So once again, if A is perpendicular to one of two parallel lines, D, perpendicular to D, and it's a pair of parallel lines, then this line must also be perpendicular to the other parallel line. And so C is perpendicular to A, and that we just quoted the perpendicular transversal theorem. And again, that states that in a plane, if a line is perpendicular to one of two parallel lines, so A was perpendicular to D of these two parallel lines, C and D, then this same line has to be perpendicular to the other parallel line, C. Example 7. In this example, you'll apply the use of parallel and perpendicular theorems to solve a cartography problem or map problem. Using the lines in the marked aerial photo of the city, explain if B is parallel to A and if B is perpendicular to C. The drawing is a little hard to see, but this is line A, this is line B, this is line C, and this is line D. And the right angle symbols are solid squares here, if you can see them, those white squares here and here and here. So we've got that given to us. They're asking, is B parallel to A? So let's take a look at B and A. B and A, all we know is that B and A are both perpendicular to C and D respectively. So, what can we say? D is perpendicular to B. That's D and B, this one right here. And D is perpendicular also to A. So D is perpendicular to B, and D is perpendicular to A. Well, if it is, then by the lines perpendicular to transversal theorem, B has to be parallel to A. If one line is perpendicular, if this line is perpendicular to this one and the other one's perpendicular to the other one, then those two have to be parallel to each other. Okay? And then what about the second part? B is perpendicular to C. Is that true? Here's C and here's B. We want to know if these are perpendicular based on reasoning. Okay, since A is parallel to B, we've already established that. A and B are parallel. So if I can put it, it's hard to see, parallel symbols. I'll do them down here. A and B are parallel to each other, and C is perpendicular to A. That's this one right here. And what does that say about B and C? So we've got one line that's perpendicular to one of two parallel lines. It has to be perpendicular to the other. Recognize that? So since A is parallel to B and C was perpendicular to A, by the perpendicular transversal theorem, we can now say that B is perpendicular to C. Finally, example 8 is a construction. It's been a while since we've done constructions. We're going to follow these directions. So I'm going to show you how to construct parallel lines. Just given one line and a point not on the line. So, construct a line through point P that is parallel to line M. Remember, when you're doing a construction, performing a construction, the only two tools that you're allowed, besides your pencil, of course, something to write with, is a straight edge and your compass. And the straight edge shouldn't be, the ruler or a ruler shouldn't be used, just the edge of the straight edge. Okay, so beginning, number 1, draw a point Q anywhere on line M. So you've got a line and a point not on the line. You need a point on the line now. You put it anywhere you want to. I'm going to put mine right here. And I'm going to label it Q. Step 2, draw line QP. So take your straight edge, put P here. Very carefully, remember in constructions, you want to be as accurate as possible so that it comes out the way you planned it. So I'm going to draw a line PQ, nice and long. Step 3, draw an arc on angle Q with compass. So this angle right here, I'm going to take our compass, put the point of the compass on Q, go up toward P. You can set it anywhere you want. I just wouldn't go too far up. Maybe about like that. Draw an arc. Make sure it goes through both of those lines. Okay, like that. Keep the setting on your compass. We're going to label these intersection points with the arc and the two lines, A and B. So I'm going to let this one down here be A, and this one up here be B. Okay. Then with that same setting, I'm going to come up here, set your compass point on P, and repeat the process in the same direction and same length. Like that. So all we did was we just took this arc, transferred it over to here. Okay. And this point right here, they asked us to label with C. Okay, 7. With a compass, measure the length between A and B. So take your compass and start at B and adjust your compass to the length of AB. Draw an arc through A so you'll know exactly where it's going. Get accurate as possible. Like that. Now with that same setting, draw an arc from point C downward. So we come all the way up here to C, put our point there, and we want to intersect, going downward, intersect that other arc. Just like that. So we went from here to there. This point right here should be labeled D. Okay, and then draw PD, line PD. Here's D, here's P. Very carefully line them up and draw line. Now, depending on how accurately you used your compass and straight edge, will kind of dictate if these really are parallel. But if you did it correctly, these two lines should be parallel. They should at least look very close to parallel. And that's how you construct parallel lines cut by transversal. So if line M and point P not on line M, then what's parallel to what? Well, we have line PD is parallel to line M. Forgot to label M.